Hi. Now today's section is symmetric key agreement. Okay. So I have already told what is symmetric key agreement. See, for example, Alice is there. Okay, and Bob is here. Okay, so they have to exchange the secret key between each other. So either they can use a KDC over here that we have seen yesterday, KDC, Kerberos, everything. And another way is directly Alice and B can exchange their session key and start communicating with each other. So that is called a symmetric key agreement. They are exchanging the key between each other without the help of KDC. Okay, so we are going to learn two symmetric key agreement. That is, first is Diffie Hellman key agreement, and second is station to station key agreement. Okay, the first Diffie Hellman key agreement. Diffie Hellman key agreement. Okay, so what exactly it is? See, you have Alice, and for this method, okay, for this method, what you need is first two variables P and G. Okay, P is a prime number which is of the order 300 decimal digit, and G is a generator variable which is of order P minus 1. Okay, so this is actually of 300 order of 300 digits. For now, for the demonstration purpose, we will take it as a small number, that is P is equal to 23 and G is equal to 11. Okay, now first step, Alice and Bob. Okay, first step, Alice first has to have choose a random number, say x is equal to, which is less than P. So here we are choosing 6, and Bob also has to choose a random number, that is 5. Okay, so this is the first step. Now after that, the second step is Alice will calculate the value of R1. R1 is equal to G raised to X mod P. Okay, and here Bob has to calculate R2, which is equal to G raised to Y mod P. So G raised to X is 11 raised to 6 mod 23, and R2 is equal to 11 raised to 5 mod 23. So if you do it in calculator, you will get this is 9 and this is 5. Okay, so now you got the value of R1 and R2. Okay, now what third step is, Alice will send this R1 to Bob, and Bob will send this R2 to Alice. Okay, that is the third step. Third step, Alice receives R2 and Bob receives R1. Okay, so now they both of them knows the values of R1 and R2. Then the next step, he has to calculate K. Okay, K is a secret key which is equal to R2 raised to X mod P, and here K is equal to R1 raised to Y mod P, which is equal to 5 raised to 6 mod 23, and here which is equal to 9 raised to 5 mod 23. Okay, so do it in calculator, you will get here 8 and here also 8. So actually what happens is they are not exchanging the secret keys as such. What they are doing is they are exchanging an intermediate result, that is R1 and R2 between each other, and they are calculating the secret key at their own place. Okay, so this is called a Diffie Hellman key agreement method, but it has its own drawbacks. One is like, see, another person Eve can come in the middle. He can select another random number and do the calculation, and finally he can also find the secret key. Correct? Then they can establish a communication and do it. No, so that is possible. That is called a man in the middle attack. Okay, so one more thing is discrete logarithm attack, which we have already discussed in previous classes. So because of these two issues, we have another agreement come into picture, that is station to station key agreement. This station to station key agreement is again based on Diffie Hellman key agreement. Okay, so we will see what it is. So till this step it is same, like they have to find R1 and they have to find R2. Then Alice will be sending this R1 to Bob, and what Bob is not sending directly R2, this is not there, but instead, you know, what he will send is, okay, what he will send is, he will attach the ID of Alice, concatenate ID of Alice, then R1 and R2, okay, then do signature, use his signature, okay, sign this message, okay, using his private key, okay, and his and what happens is he has to and yeah, the signature, and what he has to do, I think this will come here. So he got the session key, and after that what he will do is he will R1 ID R1 R2, then do the signature, okay, then do the signature with his signature of Bob and encrypt this using the session key. Okay, clear? Now this message will be sent to Alice. Okay, now Alice, what she does, she got this message, then she calculates the session key, okay, and after calculating the session key, okay, if Bob's signature key will be verified, okay, this will be verified, and what she does is she concatenates, what happens, you don't need to do it here, this will be done, Bob find the session key, then he created this message and will be sent to Alice. Alice verify this signature and find that, okay, this is coming from Bob. Then what he does, what Alice does is, she will concatenate ID of Bob, then ID of Bob, then R1, R2, again she encrypted this with her signature, okay, she signs this message and encrypt with the session key, okay, now send this to Bob, okay, Bob received this and Alice's signature is verified, okay. So this is the additional step we have in station to station key agreement. So till this step it is same, R1 will be sent to Bob, but what Bob does, Bob finds a session key, and what he does is he attaches the ID of Alice, then R1, R2, and does his signatures, sign this message and encrypt it with the session key and send this to Alice. Now Alice verify the signature of Bob, okay, then what she does is she concatenate the ID of Bob, R1, R2, and sign this with her private key and encrypt the entire message using session key. So Bob has to verify this. So in this scenario, because of this additional signature part, okay, no man in the middle attack is possible, because if Eve comes in between, she is not aware of the signature of Alice or signature of Bob. She can't verify both, okay.